Welcome to this lecture. We are solving partial differential equations with the help of a built-in solver provided in the framework of MATLAB named as PDE tool. So far we have solved elliptic problems. So today we would like to solve some parabolic or hyperbolic problems. So before that, I would like to give a review of the classification of partial differential equations. So a second order partial differential equation can generally be written as in this form. This is the most general form of a second order partial differential equation where the coefficients a, b up to so on e, they could be taken as constants or they could depend upon space coordinates x, y, or more general, they could depend upon u, in which case the equation will be a non-linear partial differential equation. So u is the dependent variable, that is the unknown. If the coefficients depend on u as well, then the equation is a non-linear partial differential equation. And I already told you if g is 0, then this is a homogeneous problem. If the source term g, this is non-zero, we say this is a non-homogeneous problem. So to classify this partial differential equation into the categories, we compute discriminant, that is b square minus 4ac. So this discriminant decides the class of partial differential equation. If b square minus 4ac, this is less than 0, we say the problem is elliptic. And if b square minus 4ac equals to 0, the problem is parabolic. And if this discriminant is greater than 0, we say the partial differential equation is hyperbolic. So I would like to give you some examples. So first example we consider where the coefficients are constants. So for example, 3 times uxx plus uxy plus 2uyy equals to 0. So if you compare this with the general form, we can write a is 3, the coefficient of the mixed partial derivative is 1, and the value of c is 2. And compute the discriminant b square minus 4ac, you would see this is going to be negative. So the equation is elliptic. It doesn't matter what is the domain. In all domains, this equation would be elliptic since the coefficients are constants. They don't depend upon the space coordinates. So in all domains, this equation has a character of elliptic partial differential equation. So whenever you have constant coefficients, it is not possible that the same equation could represent different characters in different domains. Let us take some example where we involve variable coefficients. For example, if we have a differential equation, partial differential equation, uxx plus 1 minus x square minus y square uyy equals to x square minus y square. Now this is a second order partial differential equation with variable coefficients. So if you write the coefficients, a equals to 1, there is no mixed partial derivative, so the coefficient b is 0 and c is 1 minus x square minus y square. Now we compute the discriminant b square minus 4ac, that would be 0 minus 4 times 1 minus x square minus y square. So this is going to be negative 4, 1 minus x square minus y square. Or you could write x square plus y square minus 4. But this is not a constant value. It depends upon the coordinates x, y that change when you move in the domain. So based on the values of x and y, the category will be decided. So if we take b square minus 4ac, if this is negative, we say equation is elliptic. Now we compute where it is positive, negative. X square plus y square minus 4 negative. So x square plus y square is less than 4. So all portions of the domain where this inequality holds, the equation would be acting as an elliptic partial differential equation. So if b square minus 4ac equals to 0, we could get x square plus y square is equals to 4, in which case the equation will be parabolic. And the last case, if b square minus 4ac is greater than 0, so we could have x square minus y square minus 4 greater than 0, x square plus y square greater than 4. So if I sketch the domain, so we have a circle of radius 2. So whenever x square plus y square equals to 4, mean you are on the circumference of this circle, the equation is parabolic. So let me take some other color. Equation is parabolic on this circumference. When x square plus y square is less than 2, mean in the interior of this disk, equation is elliptic. And outside this, when x square plus y square is greater than 2, this would act as a hyperbolic partial differential equation. So if our domain omega is this rectangle in which this circle of radius 2 lies, then we say outside of this circle, this is hyperbolic, inside this is elliptic, and on the circumference, this equation is parabolic. So whenever you have variable coefficients in a partial differential equation, then it is possible that the same equation represent different character in different portions of the domain, as is depicted in this example. Let me solve one final problem. There is very important equation, 2D velocity potential equation. That is 1 minus m square times second order derivative of u with respect to x plus uyy equals to 0. So what are the coefficients? A is 1 minus m square, where m is some parameter, some physical parameter. B is 0, there is no mixed partial derivative, and C is 1. So let us compute the discriminant b square minus 4ac, that is going to be this. So we have negative 4 times 1 minus m square. So if m equals to 1, then of course this discriminant is equals to 0, and the equation would be regarded as a parabolic equation. And this is called sonic flow. If m is less than 1, so if this term is less than 1, then of course square would be also less than 1. So this will give rise to a negative discriminant. Then equation would be elliptic, and the flow will be treated as a subsonic flow. And the last case, if m is greater than 1, then this quantity would be negative, and when you multiply it by -4, you will get some positive quantity. So b square minus 4ac would be positive, in which case the equation would be treated as hyperbolic PDE, and the flow would be called a supersonic flow.